all of you. Yeah, it's a part of our international conference on power, environment, and intelligent systems. To introduce a little about our conference, that we started thinking that we shall make a conference after 3 or 4 years. We did it on 2023. Now we are doing it again. In this year, we have chosen the topic as power, as we are electrical engineers, power will come first. And also intelligent systems, we cannot survive without intelligent systems. But our Honorable Director Sir is also concerned about the environment, pollution, etc. And we hope that environment is a subject that is related to all areas. So we have we have merged environment along with power and intelligent systems. So our topic is power, environment, and intelligent system. I hope this is the first edition. We hope that this will continue in the third and fourth, second edition in future. So we are fortunate. Suddenly, our Honorable Director Sir has called me and informed that 2 big persons are coming or attending another big event that is going on, organized by Civil Department. So we should take the opportunity to get to meet them, to interact with them. So we are really thankful to our Honorable Director Sir for providing this advice at right time, at right moment, because we have to do some pre-conference workshop and tutorial. So we have planned it as a pre-conference tutorial, as a part of pre-conference tutorial. And I want to mention that you know that IEEE and IIT is our co-sponsor. IIT is our technical sponsor. IEEE, some people of IEEE will also attend our conference. So again, we are getting another IEEE Smart Village person. So he will guide us. He will deliver lectures as well as he will guide us how to start. What is the importance of professional bodies starting student chapter. We hope that our students will be encouraged, and in near future we shall be able to open a student chapter in this department and in this institute. So this will be, I think, a good opportunity. And another point is that our madam is working in the field of power electronics, drives, EV. You know that this is a very important area of electrical engineering. So I hope also that from our lecture we shall benefit all participants. Those who are from outside attending online, they will also be benefited from these sessions. And also you will get opportunity to interact with them. So let's see how we can utilize this. So once again, on behalf of the organizing committee, I am really thankful to Honorable Director Sirs and our distinguished guests for giving time for us. So thank you. Enjoy the session. I hope we'll learn a lot and definitely will benefit from this session. Thank you.
May I now request our Honorable Director Sir to kindly come forward and felicitate our esteemed speaker, Dr. Sashigi Kotai. May I now again request Director Sir to kindly felicitate our esteemed speaker, Professor P.V. Isha. Thank you, sir. Now I would like to request our Honorable Director Sir to kindly address the gathering.
A very good morning to all, and also good morning, good afternoon, and good evening to all those who are online, wherever you are on the globe. I wish all the very best for the international conference on power, environment, and intelligent systems. Your HOD has said that he has incorporated environment because I was present. I would strongly suggest that on date, any engineering intervention or innovation which we do in engineering, it has to have an integrated approach, without which no engineering field can be standalone. For example, yesteryears we used to consider that we have no relationship. Civil engineers are civil engineers. The electrical engineers do whatever the electrical engineers feel like. The mechanical engineers always do whatever they wanted to do. This is not the current trend in engineering practice. We do have an integrated approach. Yesterday also we had a lecture by Professor GKCIET in the introductory session of the conference on technology for rural development. This was one of the prime points which he had stressed upon. An integrated approach is the one and the only one with which we would be in a position to practice engineering in the field. And a fair amount of commitment to the communities and a connection with the community is what is essential for practice of engineering, especially in our country. And I'm pretty confident that the international conference which is to follow is going to derive very good sessions, and it is most appropriate that we did have a pre-conference tutorial onto the issues which we are going to discuss in the main part of the conference. Well, of course, our speakers may not be available at that time, but definitely they would be in a position to give us some food for thought, at least for the next 3 years, 3 days, before we start with our major conference. And I wish all the very best for the entire activity of the international conference and the pre-conference tutorial. Professor Sujit has not introduced the speaker. We did have a relationship with the speaker at GKCIET. So one of the student projects with Professor Chiranjeev Sain in the last year could bag the 4th position in an all India competition under the Smart Village project of IEEE. And we have also been made our presence felt in that competition, and in an all India level screening we could come in the first 10, and precisely we stood at the 4th position. And that was a great achievement which I thought for GKCIET to make. And in fact, when we were trying to take it forward, I did tell Professor Chiranjeev Sain and the entire department that we should take it as an opportunity to have as many student chapters in the institute. And I'm a strong believer of the fact that no conference, sorry to make that statement, no conference organized at the department level, no intellectuals brought to the institute is going to make any change in the system unless and until our students, they by themselves take it up as a challenge and taking it forward. And I strongly believe that student chapters of these professional societies would be giving us ample opportunities to do that. And IEEE is one such professional society, as Professor Sujit has already made a mention of, which would be giving you opportunities for taking up such socially relevant projects and taking up scientific themes into our day-to-day deliberation, And that's the only way in which we can put our engineering activity to disseminate the information, vis-a-vis putting our engineering knowledge to practice. So I wish all the very best for this pre-conference tutorial vis-a-vis the international conference to follow. Thank you very much.
Thank you, sir. Now, it is a great honor to introduce our keynote speaker, Dr. Sashike Kotail. Dr. Kotail is a distinguished academician and researcher in electrical engineering, known for his extensive contribution to renewable energy, smart grids, and energy management. He has been associated with premier institutions such as Amrita Vishwa Vidyapeetham and has also served as an adjunct professor at Tejpur University. He currently serves as the Vice Chair of the South Asia Regional Committee of IEEE Smart Village, where he actively works towards promoting sustainable energy solutions. With over 130 research publications, numerous invited talks, and involvement in several impactful national and international projects, his work has significantly contributed to the energy sector. His contributions have been recognized with the Kerala State Energy Conservation Award. We are truly privileged to have him with us today. So we warmly welcome you and request you to kindly address the gathering.
Good morning, everyone present here. Not to add much to what Dr. Sibi said. Anyway, we'll be discussing more on the specific topic. But I noticed 2 points. Number one, that to practice engineering, we cannot do in a disciplinary way. It has to be interdisciplinary. Any engineering practice, any project, this is what electrical project or any electrical work, we cannot do without incorporating other basic engineering principles, not only basic engineering principles, these days advanced engineering principles also. Doesn't matter whether electrical or mechanical or civil, in any branch. So that interdisciplinary approach we need to acquire when we are students. Of course, as faculty, we need to further learn it and enhance it. But that is one thing that we have to keep in mind, that always we need to be interdisciplinary. Yeah. Then the question may arise that, okay, why in the undergraduate system, why are we learning only subjects related to our own discipline? Because if you compare the last 50 years or say 70, 75 years of engineering education, in every decade, some subjects, common subjects will come out of the curriculum and more specialized subjects we are adding. Well, to discuss it and debate it, that's altogether another thing. The only answer I want to give it is that don't think that any graduate or undergraduate program, it's not expected that within the curriculum or within the classroom, we are इतने करने से होगा उसमें अच्छा ठीक है थैंक यू so the issue is that see I was an engineering undergraduate student 50 years back. Those days things were very easy. I need to attend a class, listen to the teacher, go to the library, refer to some books or read some books. That's all. There was no other inputs available. You know that that's not the case with you. Yeah. You may feel that, okay, sitting at home or in your hostel room, you are free to ask ChatGPT, or you have to get every university will be having a teacher, an online teacher, means AI teacher who will be helping. But I will say that it's not easy that way. It has become complex and difficult because with n number of learning opportunities around you, you are supposed to intake from all these. That is where the challenge is. And that is why most of the subjects, out of the entire knowledge required for an engineer, maybe 10% or 5% are coming through your program, through the classroom. The rest we need to accommodate. But then the question is that, okay, then what is the very need and necessity of this training, in classroom training?
That is to orient you along, just give you the language of engineering. That's the only purpose. All the learning has to come outside that. So take care of it. This is the requirement in future, not only for students, for the teachers also. The second point I want to tell is that regarding Dr. Sibi said that any program means a program in the sense that you get an opportunity to listen to someone or a knowledge intake other than the regular arrangements here. It's not sufficient or it's not important at all if something is delivered in the campus unless and until it's followed up. It's very true. So this following up, if you follow up, okay, there will be some use of it. Otherwise, the intake is 0%. But I differ in only one thing. Everywhere we used to ask the students, okay, something is done, students, you take note of it, you continue learning, you follow it up, and you learn. This is what we teachers say. That is of no use. If and only if the teachers, the faculty are present with the students. When I say present with the students, it doesn't mean that you have to sit together. These days, the presence can be felt or affected in very many ways. You know it in the digital world. But I do repeat that unless and until the teachers are present with the students cannot make any follow up, the students cannot do the learning. And for the teachers, the most benefit for any teacher is coming from this association with the students. I had 40 years of teaching experience. I'm not teaching these days, but when I look back, I will say that as a person, my only asset or my major asset is my past students. Yeah. Even now, if I need anything, I depend on them. I'm totally dependent on them. But whatever learning, why they are responding to me, yeah, that's only because they have a feeling that when there were students, when they were in the campus, all our students all through, when they were in the campus, I was with you. I used to insist that my PhD scholars should accompany me to come with me if I go for any useful conference, international conference. Hell, every conference is not useful, but if a really conference is happening somewhere, it's not sufficient that the scholar is going alone, a student is going alone, presenting a paper and coming back. The teacher has to be with him or with her. Then only that will be useful. And that is where the teachers, maybe at a later stages, whatever benefit, whatever achievement they can get, they can make. That's only with only from the students, only through the students. So nothing more to say. I thank everyone in this department. This department, as Sibi said, the department is not new to me. Through saying I was associated with you last year, I think there were other applicants also from here. I do not remember exactly. And this connection, we will continue this relationship. Thank you all.
Shall we give your presentation to people now?
वही होगा.
Yeah,
Presented now? Yeah.
so continue now.
Yeah. Yes. We continue. That's it. ഇത് വെച്ചോളൂ. ബാഗിനകത്ത് ഇതുണ്ട്, ലാപ്പ് ഉണ്ട്. എടുക്കണോ? ലാപ്പ് എടുക്കണമെങ്കിൽ എടുത്തോളൂ. So shall we start? Yeah. Uh, yeah. What I have planned for you, maybe next half an hour or 40 minutes, is a presentation on renewable energy integration. Renewable energy integration into electric power system. This is the topic. But then this has a special reference to intelligent systems. That is what is your conference. Renewable energy integration in future. Renewable energy integration is happening today all over the world, in our country also. But what will be its level or quality or challenges in future? That is what, based on just three sectors. First is the solar energy, solar photovoltaic. Next is the wind energy, and the third is energy storage. Based on these three sectors, very briefly, we will discuss the integration challenges. And there is a need of intelligent systems for the future renewable energy integration. Where is that intelligence required? I'm not talking about intelligent systems, but the need for intelligent systems in future energy, future renewable energy integration. This is what I'm planning. Next slide. Yeah. So to start with, let's have a very brief look at the history of development of energy systems. Energy system in the sense that energy system means that is the production and supply of energy. It's not only electricity, all energy systems. But this has a specific context, for electrical energy, because gradually, earlier, or say some 25 years back or 30 years back, that is at the close of the previous century, maybe of the total requirement, commercial need of energy, electricity played just one fifth, 20%. Major role was that of fossil fuels, means oil mainly. It's changing now. As a part of energy transition, I hope all of you understand the term energy transition. We are planning a transition from fossil fuels towards renewable energy resources. So, since the transition is started, once again, globally, everywhere, the transition is started, and as part of that, we have to move away from fossil fuels. So most of the applications of fossil fuels, so fossil fuels were used, or even now it's being used for production of electricity. But more than that, it is for heat energy and for motive power. That responsibility also in future, electricity will have to take up. What do you mean by that? We need, so far we had diesel and petrol for vehicles, but in future we need to have vehicles using electricity, maybe from battery or from fuel cells, whichever be. We have been using fossil fuels, once again, oil or coal for heat, industrial heat. Even for cooking also we were using fossil fuel. That responsibility also will be going to electricity. So the role of electricity will be increasing. So here, what I'm showing, there are three blocks. The left bottom corner, that is the primitive state of energy supply. Primitive means pre-industrial revolution. Prior to industrial revolution, we didn't have much use of fossil fuel. Our energy resources were natural, renewable energy only. It was sustainable system what we had. But then through the industrial revolution, that was the first energy transition happened. Through several decades, the transition to fossil fuels happened. And its main feature of this transition was that energy production and supply was monopolized. You know that oil, uh, uh, the countries which supply oil, very limited, but they have a monopoly. The companies, they have a monopoly. Of course, they have a dealer distribution network, but there's a monopoly. How was electricity? Electricity boards, maybe public sector, but it's a monopoly. Only in 2003 in India, production of electricity by other than electricity boards that was permitted. Then gradually, so self-generation is now happening when we are moving into renewable energy sector. So otherwise, the middle part, that is where large scale production of electricity energy from fossil fuels have been happening, and the problems started. In the 1970s, we started realizing that there are issues if we burn fossil fuels. It was 1973, 72, 73. That's the first, the Stockholm Conference and the first book written. They were all discussing the pollution, atmospheric pollution caused by burning fossil fuels. Then gradually in 1990s, we realized that, okay, this pollution is causing a global warming. And what could be done? In between, in 1980s, actually, the search for alternatives, means renewable energy resources that started. But by 90s, we realized that it's not that easy to change over to fuel switching, we called those days. It's not easy to change over to renewable energy resources. So we need to conserve energy. That's how energy conservation, that was given top priority. We expected that the energy efficiency will be increased and the use of energy resources will be reduced. That did not happen. Energy efficiency, of course, increased. If you remember, wherever you look at these days, you are seeing only LED lights. That was not the case 20 years back or even 10, 15 years back. Yeah. But energy efficiency, LED means that is efficient lamps. Every sector, motors, efficient motors. That's all happening these days. Even fans, you have not done it, but soon everywhere BLDC fans will be coming. That's efficient fans, wherever efficiency is increasing. But what we realized is that even with increasing efficiency, the conservation is not really happening. The demand is increasing only. So that is where a very drastic decisions were to be taken. Means in the first decade of this century, 21st century, we started witnessing uh, um, the effects of climate change. So that is increasing. Everyone, there used to be debates in the last decade of the previous century or in the first decade of the present century, people, even at national level, international levels, national leaders, political leaders, they used to discuss whether it is climate change is happening or not. Today, no one is discussing that. Everyone is clear about it. So it is imminent that a second energy transition is to happen. So that is what is the right side top transitioning. When we are transitioning to renewable energy, then that renewable energy based systems, especially electrical systems, if you look up, we had a traditional power, centralized power generation. That's what we had, whether it is fossil fuel based, that's coal based, or uh, hydroelectricity, hydroelectric stations, both were centralized. Hydroelectricity is not polluting to that extent compared to fossil fuels, but we cannot expect large hydropower plants in future. Yeah. For all these reasons, it has become that essentially we need to change over to renewable energy, and we have identified only two resources for renewable energy which are matured enough, commercially acceptable or commercially available. That is solar energy and wind energy. So it is based on that the energy transition two is being planned, the second energy transition, and its effect is that when we are having the resources, energy resources, which is distributed everywhere. Fossil fuels were not distributed. That's why we had centralized power plant. But solar energy, it's available everywhere. Wind energy is also distributed, not available everywhere, cannot be trapped everywhere, but it is still distributed. So decentralization of the production happened. Go to the next slide. IEEE Power and Energy, there's a journal, there's a magazine, Power and Energy magazine. So IEEE has defined this energy transition with a 4D. That's what you are seeing. Decarbonization is the first D, decentralization is the second D, democratization is the third D, and digitalization is the fourth D. Four Ds define the current energy transition. So decarbonization means that is why it is because of the climate change. There are two motivation. Major one is the climate change. Yeah. How to avoid the climate change or the mitigation of further future hazards because of climate change. That is decarbonization. Reduce the carbon emissions, the first part. Decentralization. If we want to adopt renewable energy, solar and wind energy, solar derivatives mainly, then it has to be decentralized generation. Third is democratization. The monopolized production is no more possible, and that format is not acceptable for the distributed generation. That's why democratization is required. It's interestingly say solar, large scale solar power production, or even before that, large scale wind electricity generation. All these are mainly happening in private sector all over the world, but it's not monopolized, it's distributed. Yeah. So that is where democratization, because when people have to participate in energy production, self-generation for their own energy or peer-to-peer. Now, when I'm producing energy for myself and if I have excess, I can share it with you, even without the utility or utility facilitated peer-to-peer sale and purchase. All these things are part of uh, um, democratization. Yeah, and digitalization. This is the third block which I was showing. Uh, that is where the intelligence is coming, artificial intelligence is coming, all controls. When you have a centralized production of energy, you have a centralized control. But when you have decentralized or distributed generation, production of energy, how can this control be effective? We cannot have a distributed or decentralized control. It's possible, but it's not effective. If I'm asking that this class is to be controlled individually by each one of you, then there will be only chaos left. So there has to be a centralization. At the same time, these need to be decentralized systems also. So that's where the digital methods or the digitalization is happening, mainly through communication. Distributed generation, distributed controls need to be communicated simultaneously with a central hub so that discipline, network discipline can be maintained. So this is the background in which the future power generation means integration of renewable energy in future needs to be addressed. What I will do, I take up each section. So first the solar, next slide. Yeah. Solar photovoltaics, what is happening today and then what is there for the future. Solar PV integration, off the shelf solutions. Off the shelf solutions means the solutions which are commercially available today. Next slide. Yeah. Solar PV systems for captive green electricity means for own generation. What are the schemes available? So these can be small or medium systems. I'm showing the off-grid scheme and the net metering scheme. So these are available in almost every state of India today. Off-grid scheme means you are having um, if you have even suppose this is your house or maybe a commercial complex or an industry, you can have generation with a solar photovoltaics and then store it in the battery and use it when you need. But these are two sources. You have the grid connection, you need to cut off, you need to change over from the grid connection to use it. That is the off-grid systems. When it comes to the net metering scheme, these two are synchronized. You have a grid supply and you have a solar power generation through a grid-tied inverter that is synchronized, automatically synchronized with the grid. And then whatever generation is there, that will be locally consumed. If there is extra, that will be exported. So dual power flow means in dual direction. Power flow maybe there may be power import or maybe power import. That's why for the net, that net import will be billed by the electricity board. That's why it's called a net metering scheme. Next. And then there is another scheme called the behind the meter scheme. So recently, this is being facilitated by the utilities, the state utilities. So where you have the regular supply from the electricity board, you can have your own generation with a battery and grid-tied inverter. So it is grid-tied means that is grid following. This will be synchronized with the grid. It is synchronized with the grid, but you have a reverse power relay. You can use this power for your local demand, but you cannot export it. So to prevent the export of power into the grid, behind the meter you can operate. Just you do not need the utility doesn't control you here. Only thing is that they don't allow you to export the power into that. So if there is a reverse power relay, that will make the control, that will regulate the generation, or that will cut off the inverter as and when required. There is a hybrid scheme where the inverter has to be, storage will be there, but inverter has to be, it's called hybrid inverter commercially. That means the inverter has both modes, grid following mode and grid forming mode. Grid forming, that is used in standalone use, grid following, that is grid tied mode. So it can switch from one mode to the other as and when required. So there is an islanding switch. That islanding switch means okay, when power is generating in all grid tied inverters, that is it's a must. And the grid supply is not there. In that case, we are not supposed to export it. Yeah, the purpose of that. And in that case, it will be isolated. If the utility supply, grid supply fails, the local demand that will be isolated from that, and from the local storage, our local demand can be met. That's where in the grid forming mode, the inverter will be operating. So that's called a hybrid scheme. Even today, the new regulations are coming where you can store the solar electricity that's produced in the daytime only in the battery, and in the evening hours, because solar electricity is available only in the daytime, but the demand for electricity is maximum during the peak time. So store it in the battery and inject it during the peak time through your inverter, again in the grid tied mode, so that solar electricity can be made available for the local demand in the night time also. Next. Then you have large power plants, solar power plants, centralized power plants. Well, we do not have this much in India, but still up to say 2000 megawatt. This is in Karnataka. There are floating solar power plants. All these are to contribute power to the grid, to help the utility power generation, either owned by them or as independent power producers. It's called IPP power generation. They can supply to the grid, and they will be serving it. Next. So these are the schemes at present available. These are the technologies commercially available for solar power. Now, what are the challenges for the future? First, solar PV plants need large area. Sunshine is available everywhere, but it doesn't mean that you can have it on rooftop. That's limited. It should be shade free, but you need vast land area, because each and every cell should be exposed to sun. You need quite a large land area. So do we have sufficient land area exclusively for solar farming, solar farms, to develop solar farms to meet our electricity demand? That is one question. If you do not have, as a state, say, for example, for West Bengal, what's your total demand? To meet that, for a significant penetration level from solar, say for getting 50% or 60% of your energy demand from solar, how much area do you need? And where is it available? If not, if it is, because if you are giving the land area for solar, you are avoiding the agricultural opportunities. You are avoiding some to some extent industrial opportunities. So otherwise, you should go for green electricity import wherever large area available. For example, Rajasthan and Gujarat, they are having enough land for producing solar energy, and solar productivity is very high in those two states. So they can generate it and they can sell it. So import it. That is green electricity import. There are such contracts available even round the clock. They will store in the battery and give it for 2 hours in the night. Otherwise, all through the day, we should use it. Such imports, that's one option. Another point is solar PV does not support peak time demand. So we need storage. So far, storage was not very significant, but henceforth, all the state regulatory commissions are insisting on battery energy storage. Well, they don't say battery energy storage, but we have only battery. There is no alternative if at small and medium levels. Even at large levels, there are pumped hydro, and other options are not commercialized. Commercialized options for storage are only two, that's battery and pumped hydro. We speak about super capacitor and all those things, but commercially, these are not economically feasible. So energy storage is essential for future. Then higher solar PV penetration challenges voltage stability at node. Wherever solar power plants, which I have shown, this penetration has gone up. Then one effect is in the noon time, say after 11 or around 12, up to 2 or up to 3 in the daytime, when the radiance is high, that's solar radiation is high. At that time, the generation will be good. Solar electricity production will be good. But the demand in the noon time will be relatively low compared to the demand in the peak time, in the evening or in the morning. The demand will be less. So when the demand is less and the production is more, what happens? You should remember that if the production, solar production is happening at the far end of the receiving, the LT distribution lines, means on rooftop, individual buildings, then the local demand will be almost met by the solar generation, solar power production. So through the lines, the distribution line from your distribution transformer up to your house or up to your building, whatever power flow, current flow was there, that will be less, or the line drop will be decreasing. So the transformer will be normally set at a higher voltage. When power is drawn entirely from the transformer at your home, you will be getting a voltage that will be the rated voltage. For that, the transformer voltage needs to be kept high because of the line drop, especially in the evening hours. But when solar generation is high and the local demand, your demand is met by solar, not much power will be coming from the transformer. What will be the effect? The transformer voltage itself, or very close to that, the voltage will be rising. That is the voltage instability. And then there is a rule, see, 9% increase. Or in some cases up to 12% increase is available. 200 from 240 to 264. That much voltage only the inverter will be allowed to take. When there is a voltage rise, a solar inverter will be made to trip. So you'll be losing the generation. Such challenges are there, voltage stability issues. And finally, another challenge is that solar electricity charging of EV, that is complex. We say for electric vehicle, we say that to escape from the pollution of fossil fuels, we are going for electric vehicle. But are we using the electricity from fossil fuels? If you're charging your vehicle from the grid, and if the grid electricity is mostly from fossil fuels, it's a coal generated electricity. So the only that the pollution is not reduced, the pollution is shifted. Instead of raising the pollution level in the cities, that will be shifted to the places where the power plants are existing. That's only happening. So then, can we have a pure solar-based or wind energy-based charging, EV charging stations? It's complex. It's not that easy. It's very costly. Go next. So let's look at the PV integration future. Next. This is the behind the meter things which I was telling you. This was done a case in Tespu University, where a 33 kV substation, under that several at LT level only you will be installing the plants, but then you need to have a reverse power flow meter, relay, and that should control each inverters. When there is a tendency for the power to go back, then with that signal you need to trip inverters one by one. That's a requirement. So this will be the behind the meter system. This will be emerging in future. But we need a management system, an energy management system, an intelligent system that has to decide which inverter has to be tripped, or even throttling is possible. So in the converter itself, the power electronics design itself, you need to incorporate a method for throttling the output. Next. Another possibility is that there is a possibility of generation control within the solar photovoltaic cell itself. Next, one more. This is the IV characteristic and the PV characteristic of solar. IV means the voltage and current. When you change the point of operation, this point of operation, when that voltage and current is maintained, you get maximum power. Any other point of operation, you'll be getting a lesser power. So it's possible that by shifting, all of you might have heard about MPPT, maximum power point tracking, extract the maximum power. But when you do not need that maximum power, you can control the generation by shifting the point of operation so that the power is less. Go back. One more. So that's what is shown here. In a solar power plant, this is the maximum power available. In a 1400 seconds window, a study was done. This was a simulation study. And a minimum power needs to be maintained. In between the actual power production, you can control by changing the point of operation. Just by installing a converter, a DC-DC converter, between the demand, the grid and the solar plant, you can do that control. Yeah. The next. This was tried in the field. This was tried, you see, in 2000, around 2010. This was published in Power Energy magazine. That's a field experiment. Even now, this system, such control system, and that is automatic generation control of a solar power plant, this is not commercially available. So this is a system. A little amount of intelligence need to be extracted from the operating system, from the energy management system, to take a decision on at which point this needs to be operated. Either it has to be based on the frequency changes, or it has to be based on the rate of change of frequency. It's called a rock off, or it can be based on the demand fluctuations. But combining all these things, there is a need to develop intelligent systems to control the generation. When the solar generation is very high and it is causing the frequency to go up or the voltage to go up, I told you about the noontime voltage stability. In all such cases, it's possible to control the generation of the solar intelligently. Next. Yeah, another possibility that will be developing in future is that you are hearing about the green hydrogen production. Green hydrogen production means hydrogen produced through electrolyzer only, but produced with the green electricity, either solar or wind. So it's possible in solar power plants we can have electrolyzer connected to that, and in two modes it can be operated. Either regulate PV terminal voltage by varying hydrogen production, or produce hydrogen at concentrate. The first case is that when you have a standalone solar system and you are connecting a load to that, we need a fixed voltage there. With fluctuation in the radiation, you cannot get a fixed voltage there, or even with a constant radiation, with the fluctuation in the load, voltage variation will be there. But these two can be controlled if you are having an electrolyzer and at a variable rate you produce hydrogen, store it, deal it separately, so that you have fixed terminal voltage. Instead of a battery with a hydrogen, with electrolyzer, you can do that. Otherwise, if your primary function is to produce a hydrogen at a constant rate, you can do that. The balance electricity can be stored in battery. Again, this concept needs to be commercialized. We need to develop a system, a controller to effect this. Next. We had some experimental basis. This was a BTech project in Amrita University, tried and proved and published a paper on this. Next. Yeah. I'm leaving citing the paper. Those who are interested can look into that. Next. Yeah. So that's the case of, so mostly in future, in solar PV integration, the generation control will be an essential requirement, and we need to develop intelligent control systems for that. Coming to wind power generation, next. Yeah. There are three technologies available today. One is squirrel cage induction generator. That is very plain. This is the oldest in the existing commercial system. Next is doubly fed induction generator. Yeah, that's again induction machine with a wound rotor machine. Today, most of the manufacturers are going for this. And there's a third technology, that is permanent magnet generator. These are the three systems. Old machines you can see are squirrel cage machines only. And the next generation, some of these machines were permanent magnet, very efficient, but the issue is that it's very costly. So again, the latest large machines, today the largest single wind electric generator machine is of 16 megawatt single unit, and another machine that will soon be made available in the market, that is for 20 megawatt single unit. Such large capacities, permanent magnet cannot compete with the DFIG. So DFIG is the leading technology. Next. I will not discuss much about it, but in squirrel cage machines, it's just ordinary induction machine. It's connected to the grid. So induction machine connected to the grid. If it is connected to the grid, an induction machine, it will work as a motor. But on the shaft, you are also connecting a wind turbine through the gear. Through the gear means, that usually the induction machine, 4-pole machine, means it has to work around 1500. That's a synchronous speed. Below that, just below that, with some 5% the slip, it will be operating. And the turbine cannot operate at such, if you can operate, but if you make the turbine operate such high speed, that is a bit challenging. That's why we are using a gear. The issue is that it gets a torque from the electrical grid, power grid. It also gets a torque from the turbine. When the net torque increases, naturally, the rotor runs above the synchronous speed, and it becomes a generator. There's a principle of that. Next. In a doubly fed means it has a stator connected to the grid, and the rotor mechanically the wind turbine is connected, but there is a rotor winding. That is, you know that the rotor winding, the voltage and frequency will be different from the stator. The slip times of frequency, the voltage also will be different. So it is rectified and use another inverter to produce grid frequency and grid voltage to connect it. That's the principle of that. And whatever slip it is operating, say it is operating at a 10% slip means of whatever power is given by the stator, 10% of that will be going from the rotor. This is near 5G, so you get extra power, and there are advantages if it is made specially designed for wind power applications. So up to 30% slip it is designed, means you get 30% extra power compared to, means above the synchronous speed only it will be a generator. So in motoring, we are giving an electrical power to the stator, and then you get a mechanical power output. And from the rotor, if it is wound rotor, the slip power can be recovered. That is the motoring. In generation, we give mechanical power input. You get a stator power output, you get a rotor power output, as we have already discussed. In addition to this, it's possible to have sub-synchronous generation and super-synchronous motoring. Well, in wind energy, there is an application for this sub-synchronous generation. That is, below the synchronous speed also it can generate. How is that possible? When you are giving a mechanical power, which is relatively less, and then if you circulate a power from the stator to the rotor, so by a rotor injection with appropriate frequency and voltage, then it can be, in that case, how do we say that induction machine is motoring or generating? That is related to the synchronous speed, the rotor magnetic field, which is leading. You have a stator magnetic field and rotor magnetic field, which is leading. That decides. So motoring means where the rotor is behind it. If by adjusting the rotor frequency, by injecting a selected special rotor frequency, we can make the rotor magnetic field to lead, that becomes generator. So that is that it can be done in the synchronous speed of the designated frequency. So below that synchronous speed, it can happen. That is the sub-synchronous generation. This will be required when the power is less, wind power is less. Next, and this is a permanent magnet machine. So where you can have instead of wound machine, so alternator, a synchronous machine, you use large number of magnets. What is the advantage of using large number of magnets? When you increase the magnetic number of poles, then the synchronous speed can be reduced. If the speed can be reduced, then even without a gears, you can connect it with a wind turbine. So that is why people go for that. This can be operated as variable speed, variable voltage, variable frequency. So rectify the entire power and get the grid voltage and grid frequency for the AC side, and that is the third technology. Next. Even this is possible with an induction machine also, squirrel cage induction machine also, means you rectify it and then again invert it. In that case, you can have a variable speed operation. This was tried, but commercial is not available now. Next. In addition to that, there are small machines where permanent magnets are mostly used. But there's a small wind turbine generators are not making much impact in the field today. In future, there may be more necessity, requirement for this. We will see that. Next. Yeah. So in future, what is going to happen? Next. Yeah. One major improvement that's expected for improving the wind power generation future is a maximum power point tracking. MPPT, all of us here, MPPT in solar power plants, but the maximum power point tracking required in wind turbine generator is different. The principle is different. The purpose is that, this is known as the power curve of a wind turbine. That is, with respect to wind speed, what is the power output? In a wind turbine, with up to certain wind speed, it's not generating. After that, it's generating. But then beyond certain wind speed, beyond the rated wind speed, the power in the wind is not fully taken. By restricting the efficiency of the turbines, we take a constant power from the input, and the rest is wasted. It's not taken. So maximum power point extraction, maximum power point tracking is possible only in this range, in a particular range. That's only turbine. It's not on the electrical side. How this can be done? And at present, commercially, this maximum power point tracking is not happening in the wind turbine machines available, but that is a requirement for the future. Next. What will be required if at all we go for how can we plan a maximum power point tracking? You know, the turbine has a power output. You have a machine, if you consider permanent magnet generator, that also, its power also can be, you know, all these expressions. This in a three-phase machine is a 3 VI cos phi, or the induced EMF of 3 EV by X sin delta. That is for the generator. And after the rectifier the DC side, its power can be expressed there. For the grid interface, again, the power can be expressed. You have studied all this formula. What I am telling is that you need to match this available power with this generator. The same power the generator should be able to absorb. So from the speed, if turbine is running at some speed, the speed of the generator is also, we can decide it from that, and that will decide the voltage accordingly. At what current needs to be extracted from this can be found out. If both these currents and voltage AC side is known, then the DC side we can calculate, and then accordingly we can manage. Next. Yeah. That is, from the basic turbine features, we can get the maximum power available that can be made available, and then equating that with the generator, we can calculate the generator current, and then from that the terminal voltage and current on AC side is available. With that, the DC side can be calculated. Proceed for the grid transfer. How much? What's the grid voltage and the reactance, and decide the modulation index for that. So ultimately, electrically, you are controlling it. All the controls will be happening in this inverter only. That is the speciality of that. Maximum power point tracking has to be done by the wind turbine, but the control is not mechanical. The control can be electrical. That's advantage, but we need to develop it. Again, because multiple parameters are involved. How to monitor it, how to track it, and how to compute it and execute it. This is the challenge for an intelligent system here. Next. Another possibility is that when you have a number of machines, we discussed that in the permanent magnet type or in the DFIG, there is a DC link. AC, DC, AC. That's a system. When there's a DC link, maybe we can have a high voltage DC link. To that, different machines can be connected, especially for offshore units. This may be more ideal. And here, in that case, even storage is possible here, control is possible here. Next. There is a major project is going on with all major global manufacturers of wind turbines together. They call it Interopera EU, European Union. That is enabling interoperability of multi-vendor HVDC grids. When you are operating a common HVDC link for different machines, the different machines are manufactured by different companies. So what are the parameters which need to be shared by different manufacturers? Usually, each manufacturer will be having all interior parameters that will not be shared. So when you go for the interoperability, then there is a need for sharing certain parameters. So this is what all the global manufacturers together, they are doing it today. Next. The hydrogen production, that is also possible with the wind. Next. Yeah, same thing. Next. Yeah, then coming to the standalone, I told you standalone machines today, small machines are permanent magnet machines, but maybe in future there is a possibility that a DFIG can be used for standalone. What is the challenge? The challenge is that if you have a load, the AC load, the voltage and frequency should be constant. So can you keep the voltage, stator voltage and frequency constant? It's possible with the help if you have a DC storage and if you have a bidirectional converter, it's possible, because this machine, as I explained earlier, it can be operated either in the subsynchronous or supersynchronous generation. If it is supersynchronous generation, means power needs to be taken out from here. Otherwise, subsynchronous generation means you need to inject a power and that needs to be circulated. Yeah. So the excess power is there compared to the loads that can be stored in the battery. If there's a deficit, the battery can supply that power. So with the two bidirectional converters, this can be done. Basic principle I'll tell you next. Basic principle is that for an induction machine, the equivalent circuit of an induction machine, you may be familiar. So it's a stator voltage you need to keep constant. For that, the only requirement is that the rotor voltage, rotor speed and the rotor injected voltage, that are the only dependent factor and the load. So if there is any change in the rotor voltage, then you can still keep the stator voltage constant by adjusting the rotor voltage or injecting a voltage at the required frequency into that. Next. So that's called a dynamic frequency tracking. So it is possible, again, commercially this is not available. The controller needs to have some intelligence. In that case, it is possible to have even DFIG for standalone operation. And the advantage is that then it becomes very cheaper. Permanent magnet machines are costly, but induction machine, is very cheap. Next. Next. Already explained. Yeah. Coming to the battery energy storage. Next. Go on. It's possible to have battery storage in different systems. So next. Even in hydropower plant, we can have pump storage. That's one option. Next. Yeah. Yeah. So battery energy storage, again, today, large scale battery energy storages, battery storage plants are being planned in major substations on the transmission side. But then there is an advantage for distributed battery energy storage. On the transmission side, even if you store, the power, what are you storing there? You are storing the excess solar electricity generated in the daytime. This generation is a happening distributed. And then you are taking this into the transmission level and storing somewhere. In the peak evening hours, again, you are taking it from there and bringing it to the distribution network. Instead, if you are having distributed storage facility in the distribution network, all the transmission distribution losses can be avoided. That is advantage. Next. So there can be two ways this can be done. One is a LT feeder with a net metering and an individual solar prosumer who produces and uses solar electricity. They can store it with a hybrid inverter. They can operate. A hybrid inverter means it can charge it, and when sun is not there at that time, you can discharge it. Means in the peak time. Individually, you need to do. Otherwise, next. Yeah, this can be done as a community bus. This is the distribution transformer. From the distribution transformer, the feeder is running. The distribution LT feeder is running. So many individual solar rooftop power plants may be there, but you don't have any storage there. At the transformer, you have a storage. It's a hybrid inverter and battery. So in the daytime, around noon time, you store it in the battery, and in the peak hours, you can disconnect from here. So individual prosumers, they can effectively, if I'm having a rooftop solar power plant, I'm not having a battery. There is a community battery, that is CBus. So there, my excess electricity is assumed to have stored there in that community battery. In the peak hours, when I'm using some electricity, whatever I have stored against my account, that is adjusted it. If, eventually, only this battery and inverter, these are installed at the transformer, and there is no operator requirement. It's only programmed against for this requirement. But at the electricity board, in the accounting, the energy accounting, the billing, they can do the individual accounts. Even the electricity boards, the utility, these days electricity is available, solar electricity is available for less than a rupee at the noon time from major power plants in India. So this can be purchased through energy exchange, and the electricity board itself can store it there and then use it in the peak time. What's the advantage? Otherwise, what the electricity board is doing today? Electricity boards are purchasing peak power during peak time from energy exchange and by bidding. So the cost varies from 7 rupees to 15 rupees in that range. Whereas if it is done this way, purchasing for 1 rupee or 75 paise, and then maybe a storage charges you give 4 rupees or 3 rupees for as storage charges, still it is much cheaper. So this is another possibility of integration for the future. But again, you need an intelligent energy management system here to manage all these things. Next. Yeah, that's a best concept I explained. Next. Yeah. No. Next. Okay. Lastly, there is, microgrids are developing. So independent microgrids. This is a microgrid I'm showing. It has an AC bus where the main source of power is wind turbine. As I explained to you, DFIG can be operated to get constant AC voltage with constant frequency. There is a DC bus, there also voltage needs to become constant. To that, solar power generation is possible. It should be having buck boost converter to control. There should be a battery, a bidirectional converter is required to control that. DC loads can be there. Even deferable loads like water pumping means when there is excess generation but no load, at that time you need to operate it. But then you need different types of controls on this. For example, this AC bus voltage and the frequency regulation, what we explained earlier, that needs to be done. DC bus voltage regulation, that is, the battery has to, you need to keep AC bus voltage and frequency constant, DC bus voltage constant. How do you keep this constant? If voltage is rising, you charge the battery. If the voltage is going down, you discharge the battery. Even then, if the battery is fully charged, then you control the regulation from the PV. Yeah. Still, if load is less, you add additional load. Otherwise, on the other side, you need to do the load shedding. And maybe if there is extra power available on the DC side, you can transfer it through this bidirectional controller to AC side. If there is extra power there, that can be transferred here. All these versatility there, but that needs 1, 2, 3, 4, 5, 6. 6 different controls, multiple controls to be done simultaneously. How will you do that? Again, intelligent systems are required for this. So these are some of the options. Go on. I've not explained it. Go to the last. Yeah, next. Next. Yes, keep it there. All these, several such schemes. I suggested a few which I've been trying, but more such things are possible, are required for the future. But intelligent systems, intelligent controls are essential for this thing. But you should always remember, I don't know whether you are aware of this TRL, technology readiness level. Whatever we do, that is at this level. Yeah. 1, 2, 3, where we are trying it in our laboratories. But then what is required is TRL 9 or 10, the commercialization. So there are several steps. Don't expect that whatever we do, that will be reaching the market immediately. So patiently we need to develop. That's where academic institutions need to collaborate with industry, because only industry can work at these levels, only academic institutions can work at these levels. In between, a collaboration. That's why we always say that this academic industry participation, all those things. So keep that in mind, that any technology development, it takes years. It's not that when you publish a paper, immediately someone will take over. No, you have to look for, you work with them, learn from that industry what is happening, and towards the end of that, guide them to that level. Next. So that's where I stop. If you have some questions, immediately you can ask. Thank you.
I want your advice that located in Malda, where this most of projects were related with wind turbine. So here wind speed is not so high.
I'm not sure the wind because this area you need to check whether the wind monitoring has been done in this area. The wind speed, because solar means anywhere you can plan, but wind means the resource assessment is to be done first.
West Bengal region, this monitoring has been done by IIT Kharagpur, but in the late part of this state, this wind turbine is not getting visible.
Yeah, that's what my understanding is, that wind speed is not that attractive, generally in West Bengal. But still, there are pockets where, yeah, so you need to identify that. And in such cases, maybe for such low wind region, the small wind turbines are more attractive. But small wind turbines, to effectively use it, we need to work on it, as I was suggesting. Today, small wind turbines are very costly. But see, if you keep a small wind turbine, charge a battery. Battery is fully charged. Still, the wind turbine will be working. It does not know the battery is full or not. So, what will you do then? So, there should be some control for that. There are several incidents in the south where the wind speed is increasing, battery is fully charged, or the load is not there. The blade is accelerating, blade is flying away and falling on somebody, killing. All such incidents are there. That is why small wind turbines are not being promoted. But for electrical engineers, they need to understand this problem, and small wind turbines can be further worked on, as I was discussing, and there is enough scope for working on that section, how we can maneuver the small wind turbines. Large wind machines may not be suitable for this area.
You don't know why in future why you will work. It means first that you are building with wind turbine or solar system. Sir, that you have mentioned that hydrogen fuel. So one problem is that hydrogen. Again, if you consider this eastern side of India or West Bengal, hydrogen production is still less. We have to import hydrogen. So hydrogen production is a certain area where grid industry
Yes.
will come.
Yeah.
But the main problem of hydrogen production is that the production cost is very high. That means electricity is relatively better. That can be tackled by you can use solar PV energy. So in this conference, the keynote speaker is coming from Singapore. He has its own electrolyzer manufacturing company. So it is good opportunity to interact with him also on the day of conference. Dr. Dolapati, former professor of University of London, and now he is heading one company of hydrogen manufacturing company. He will come. He will address you all those problems. But here, sir has demonstrated that one solution for hydrogen production, you can take the help of solar PV, but still there are lots of challenges. Sir, from my institute, my advice, I request advice that if you want to start some project work, that we shall create one hydrogen production unit with the help of solar or conventional energy. So, where we can apply for funding or other things.
Yeah. For green hydrogen production, now there are several funding agencies, both Ministry of Power and MNRE. No, both are interested. In fact, you can discuss with Webrina itself. In every state, the renewable energy department, they are given this task of promoting green hydrogen production. So, as a research project, you can propose where actually, as you rightly said, for green hydrogen production, when you are resources okay with the solar, but how will you control and regulate the production, and what are the safety precautions you need to have in that? There actually your power electronics has to help. You need these controls, because one thing is that okay, when the radiation is much less, how to extract a full power for the hydrogen production. Usually we work on MPPT, maximum power extraction, but you will require an optimum power extraction, sort of OPPT for such application, where they, as you rightly said, the electrolyzer is very intense, power intense actually. So how to control it within that limit to help that actually this interfacing controller converter has to help its control. So such projects you can think about that at a nation level. As I told you, commercial level that will take much more, and even if you apply for a commercial level production, it will be difficult for you because you do not have any background in that. To start, actually, research projects you have to concentrate where
You can board a plant, solar with a small electrolyzer, and it's controlled. And even as I told you, it's not only electrical. Once hydrogen is produced, the issue is that where to store it and how to store it. Even absorbents are also there. So mechanical engineering and chemical engineering or chemistry, all these departments can collaborate in that. Then only a project will be. If you think of any project, think of an interdisciplinary. Collaborate with other departments and to develop it. First thing is to know what is happening in green hydrogen, what all the works are going on, means the literature survey. From that, you will be able to join where you can join with your interest and with your facility. Ah,
Thanks. For this is very nice, very informative, and I need some suggestion regarding the net metering. Actually, in our institute, we are going to plan like net metering kind of thing. So that is the we are using now. Right? So with that, we have the scatter kind of like buildings, right?
yeah.
So we have the scatter area. So on the top, it will install all the solar plates. Our suggestion is so from here.
I understand your question. Yeah. It's possible. It's possible. See, you have a substation. Ultimately, now the first thing is that, please say, first thing is that whether the West Bengal Energy Regulatory Commission, whether they allow net metering scheme for a commercial consumer. They are allowing it. Okay, good. In our state, it's not allowed now. So if that is allowed and within that capacity limit, whatever you are saying that, their requirement is that you have a substation, 11 kV or 22 kV. What's your incoming feeder? 11 kV. 11 kV. So there actually on the LT side metering you can opt. LT side you need to install a net metering. But then you can have the plants on rooftops of different buildings, no issue. At the net metering point where the meter is there, the final transaction will be happening. What they want to know is that how much energy is exported and how much energy is imported. This is available from the net metering. The challenge is that if you have some installation here, there will be one inverter here. And in every building, there will be an inverter. So if you put all these generation into the grid, in the DB, distribution board, you are not carrying this inverter output to the substation. The respective distribution board matching that capacity, you are doing that. Your DB is having a cable connection from the substation that has a power capacity. Your inverter should not be producing a power more than that. That's what you have to see. So that part is okay technically. The issue is that electricity board will say that we want to see how much solar you are generating. In the net metering, it is the net power flow is happening because your generation, part of that it is used here. If that generation is more than your present consumption, that excess is only exported. So the exact generation is not measurable in the net metering. But the electricity board will insist on the solar generation. Means each inverter, it's a display, power generator. That display should be made available in the substation. So without having power connection extended there, you can have distributed this grid tie in the network. That is, the inverter will be connected to the distribution board, but that inverter will be having an energy meter either through Wi-Fi or there are different communication systems, whichever a cloud you can opt. Through any system, you can have a display meter there. For each inverter, a display meter will be there. That display meter means a single meter. You press one, inverter one, the reading. Press two, inverter two, the reading. Finally, the combined reading of all these inverters. With that, they will be happy. So what's the total solar generation? What is the net import? What is the net export? These are the three readings in the final electricity bill is required. So that way it is possible. Solar developers are doing it these days. You can very well go for that. That otherwise, if you install in different places, like it was being done earlier, and carry all the cables up to substation means very costly. That is not required. Behind the meter itself, you can connect and you can do that. I'm doing such a project in a medical college in Kerala. So it is possible. That is where the smart system, the communication system, the smart, that the word is coming mainly for communication. So you can have distributed meters, but that can be carried. From the electricity board, when their meter reader comes, they want all the meters together in one. That should be in the substation. This is the requirement. So it's possible now. It's possible now, and there is one more challenge. I do not know again your regulations. In other state regulations, whatever you have generated in the daytime, If you're using it in night time, then there will be a penalty for that, means a reduction. In our place, 33% reduction will be there. Otherwise, you have to install, means depending on the capacity, battery storage, best. So first explore that what does the regulation say. If there is a mandate on battery storage, install that battery. So your inverter should be hybrid inverter. That battery installation you can do in the substation. Battery will be connected through a hybrid inverter. So daytime that will be stored. The night time you can program it, say for the peak time hours alone, or for the entire 12 hours. How much power should be supplied from that? If there is any mismatch, again export and import will be happening. No issues. If there is excess power you're importing, exporting, you'll get money for that. So all these are possible today, but very few people are aware of it. Perhaps Surajit, actually, what we need to discuss with the teachers and students with all, not only electrical engineering principles, but the business regulations also. Without knowing that, you cannot do any useful research, as I told you. And if you are aware of that, then you will know, okay, as I told you, an energy management system which enables all these things, different buildings, is not available in the market today. That is something through a project you can build and utilize it. But to do that, to know that, you should have some practice of doing this, commercially doing that. Seeing that only, you will be learning, whether teachers or students will be learning what is the requirement and developing it. So you can very well go for the net metering system. Yeah, because you have to start from that lower level and then learning from the system. You can finally, at least you can have demonstrate in your campus, and then with industry interest, you can show that see this is what we have selected and it's working here. The rest, that see there is something that is the what do you call when a laboratory developed a circuit, that its durability will be much less. But when the industry, when they do, their practice is altogether different. That will be at commercial standards. We do not go by standards. That's the issue. Industry has to go by standards. So the two levels are of course different, but at your level you can do that research. So I think I have taken enough time. Let me thank all of you for the patient hearing, and in future also for any such interaction, I'm available. Thank you.